Hey everybody, so we are going to be working through a projectile problem, and this is the first of our two types. So we'll do a projectile, and then we'll go ahead and also do a 2D motion problem. So our projectile problem statement reads, a projectile is launched with an initial velocity of 13 meters per second at an angle of 41 degrees. Find its total horizontal displacement and travel time, assuming that it lands at the same height it was launched from. All right, so again, as we've done before, we can set up the first part of this problem by considering that we have some angle of launch, and we'll draw that here. So our angle is 41 degrees, 41, and our initial velocity VO is 13 meters per second. Now, that initial velocity, because we care about two dimensions, we want to look at our x and our y dimension and see what that velocity is for the y part of it, Vy0, and the x component, or x part of it. This is Vxo. So we'll be able to find those two things using trigonometry and the fact that we know our hypotenuse of this right triangle and one of the angles. So to do that, we're going to start by looking at sine and cosine. Sine, of course, is sine of our angle 41 degrees is equal to the opposite over the adjacent. So the opposite side is Vyo. I said the opposite over the adjacent. What I should have said was the opposite over the hypotenuse. So we have our opposite over hypotenuse because we have SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So finding our sine, we take our opposite side, Vyo, and divide it by our hypotenuse. So that'll be 13 meters per second. Now to find out what Vyo is, we simply need to solve for it and multiply 13 times, so 13 meters per second, times the sine of 41 degrees. Equals Vyo. So our initial y velocity, let's grab a calculator. I'll go ahead and punch that in. So we're going to take the sine of 41 degrees. Make sure your calculator is in degrees mode for 41 degrees. So the sine of 41 is 0.65. I'm going to multiply that times 13, and I get 8.53. So our initial y velocity is 8.53 meters per second. We can tell the direction of that by looking at our triangle and saying, okay, I'm launching straight upwards. So by projectile here, the portion of this that's going straight up is Vyo. So the part of our total initial velocity that is directed upwards is Vyo, 8.53 meters per second, up. Now we still need to find how much of this 13, or the total velocity, is in the x direction. So to do that, we'll take cosine of 41 degrees, which is equal to the adjacent side, Vxo, over our hypotenuse, 13 meters per second. Again, we can just multiply and take 13 times the cosine of 41 to get Vxo. So 13 meters per second times the cosine of 41 degrees is equal to Vxo. So doing the math there, cosine of 41 is 0.75. We're going to multiply that times 13, and our x component is 9.81 meters per second. So our x component to the velocity, again, we can look here and see that's going to the right, so we can draw an arrow for our direction. And Vxo is 9.81 meters per second to the right. So these two values will help us get what we're looking for. And again, ultimately we need to find our horizontal displacement, delta x, and we also need to find our time, t. In order to do that, we're going to have to use this x and y velocity in our equations of motion. So if we recall for projectile motion, we're going to write our second equation from the sheet. So delta x equals vx0t plus 1/2 axt squared. Same thing for y. Delta y is equal to vy0 times t plus 1/2 ayt squared. Now before we go and solve these, I'm going to take a step back and we're going to look at what we know about projectile motion in general. So for any projectile that follows the path described in our problem, where it lands at the same height it was launched from, we can draw the path like so. So it follows a curved or parabolic path. The starting height, y initial, is the same as the ending height, y. So our initial and final heights are the same. Also, we can say that for a projectile in the y or vertical direction, the acceleration that it will experience is due to gravity. So we have ay equals 9.8 meters per second squared. Now, we should define, if we're saying that up is positive, which I think we should, so we'll say that up is positive and to the right is positive. So this gravity should be a negative 9.8 meters per second squared because it is acting down opposite to our positive direction of motion. For the x direction, another thing we can say is the only thing that would slow down our projectile is air resistance, and we are going to ignore air resistance for this problem. So ax is going to be 0. So these three things, we know that if y equals y initial, then delta y, which is y minus y initial, must be 0, which makes sense looking at our picture. The change in height for this projectile from beginning to end should be 0 because it lands at the exact same place it was launched from. So these three items that we know, ay is negative 9.8, ax is 0, and delta y is also 0. We can put those into our equations over here and they'll help us out. If this a subscript x, this acceleration in the x direction is 0, this entire last term on the right will just go to 0. And we'll be left with our x equation as delta x equals vx initial times t. Likewise, over here, we know that delta y in this case is 0, so we can get rid of that. And we know that ay is just our gravity. So ay is negative 9.8 meters per second squared. All right, so we're going to do a little more work with this y equation to get it simplified down. First, I'm going to go ahead and multiply this out. So 1/2 times negative 9.8. So now we have 0 equals vy initial t. And of course we have 0 because our delta y just became 0. We said that we have no change in height. And then vy initial t plus a negative 4.9 meters per second squared times t squared. If we simplify this further, we can move this entire term on the right over to the other side. And because it's a negative, we'll add it and it'll become positive. So we'll get 4.9 meters per second squared times t squared is equal to vy initial times t. Now the one last thing we can do to simplify even further is to divide both sides by t, because we've got a t over here and a t squared here. If we do so, this t will just cancel out, and this t squared will become just t. So our final version of the y equation will be 4.9 meters per second squared times t is equal to our initial y velocity. All right, so now we've got two workable equations that we've simplified down, and this is your simplified x equation for projectile motion as we have it here, landing and launching at the same height. And this is your y equation simplified for that same problem. So we're going to use the Vy initial and Vx initial that we found in these equations and see if we can solve for delta x and t. Now you'll notice this first equation has delta x and t in it, so we won't be able to get very far right away with this one. We could put our Vx initial in as 9.81 meters per second to the right, but we can't really solve for delta x or t just yet. So we should probably start with our y equation. So looking at this, 4.9 times t, let's put in our Vyo as 8.53 meters per second upwards. If we do that over here, 4.9 meters per second squared times t equals 8.53 meters per second upwards. Now that 8.53, we're going to solve for t here because that's our one unknown variable, and we'll go ahead and divide 8.53 by 4.9. 4.9 meters per second squared. Also notice our units here. We have meters per second divided by meters per second squared. The meters will cancel, one of the seconds will cancel, and we'll have 1 over seconds. So we'll get units of seconds, which is good because we are solving for time, and time is in fact measured in seconds. So 8.53 divided by 4.9, and for t I get a time of 1.74 seconds. Great, so we just got one of the two things that our problem statement asked us for. So we solved for time, one of the unknowns. That is fantastic. Now we can solve for the last thing that we need to know, which is delta x. So if we put in 9.81 for our Vx initial, and we put in our time of 1.74, let's see what our delta x will be. Delta x equals 9.81 meters per second to the right times 1.74 seconds. Our seconds will cancel out, seconds in the denominator with seconds in the numerator, and we just get 9.81 times 1.74, which gives us 17.07 meters. Of course, our direction is still valid. In our x direction, we are moving to the right. So for our displacement, we'll report a direction as 17.07 meters to the right. So this is how we go through, and starting with an initial velocity and an angle, we solve for the time and the horizontal displacement for this projectile. All right, in our next video, we're going to look at how to do it in reverse. So if you have a time and a delta x, we'll start with these and see if we can get back to where we started.